Perfect. Welcome, everybody. I'm very excited to be here. My name is François Michonneau. I'm located in France today. It's the first time I have the opportunity to present to the Latin art community, and I'm very happy about that. I think it's a very vibrant community, and it's great to see all the things that people are doing in this part of the world. So a little bit about me. I was recently working at a company called Voltron Data that was creating a database system, basically. And I worked there for about 2 years. And just before that, I was working at the Carpentries. Even before that, I got a PhD in marine biology. And one of the last projects I did was working with these very large data sets, and that were not that big, but big enough that it was annoying to work with them in R because I was always running into issues. And I really wish that at that time, tools like DuckDB and Arrow existed, because it would have made my life much easier. And now that these tools exist, I really like to share or to use them to make other people more productive. So it looks like people are still joining. I think we have about 20 people who are signed up, but we're going to get started. And first, I'd like to start with a little icebreaker. So I have this link here. Let me see if I can put this in the chat. Oops. If you have your cell phone nearby, you are welcome to scan the QR code. Otherwise, let me put the link to the poll directly in the chat. Making sure that it's open here. Activate. Here we go. So the first, I'm asking you a few questions. I would like to know where you are located today. Where are you joining? I'd like to have an idea of the representation we have. Then I'm asking if you have already used DuckDB or Arrow. If you are working with data today, what type of format do you typically have it in? And last, an open question about what you are hoping to learn today. Are people able to join the chat? Can you put a thumbs up in the reactions to make sure that people can access the poll? Okay, thank you. Perfect. Okay, Argentina, Chile. I've been trying to learn Spanish, and I hope that in a few years I'll be able to give this talk in Spanish, but right now I have to do it in English. We have someone from Germany. Excellent. Content missing. Can you explain what you mean, Mauro, by the content missing? I think it's click on Start Survey button. Okay. Thank you for the tip here now. We're going to give one more, a few more minutes. is DuckDB. OK, excellent. So we have people from lots of places. That's good to know. It looks like about a third of you have already used DuckDB. We are at closer to 50-50 now, but right now still a majority hasn't used DuckDB or Arrow. There's something, you can see this. Oh, OK. Interesting. About as many people are using data in Parquet file and CSV, so that will be good to see. And it looks like a lot of people are interested in learning more about DuckDB. So that's good to know. That's great. We are going to do that. Today we are going to spend a little bit of time on a lecture-style presentation. So I'm going to go through some slides, give some background around DuckDB and Arrow and what it means when data is larger than memory, and some strategies we can use to work with this type of data. And so I thought to be able to do the tutorial, we're going to use real data. Obviously, I didn't want to use a huge data set because I didn't want you to spend a lot of time downloading very large data sets. So I created a small version of a data set that is much larger. And the code we write today could be used on this much larger data set. So if after the tutorial you want to try on your own to run the same code on this very big data set, you'll be able to do that. But today, just for the workshop, we are going to work with a smallish data set. There's still about 70 megabytes of data to download. So I thought that we could start with that, and so we can let the data download as I go through the lecture. Let me see if I can screen share a different window. Close this project. Do this. Let me just a second. I need to switch the window I'm sharing. So the first option I suggest you do is to use RStudio and use the Git project. So if you go to File and you do New Project, you can click on Version Control here and choose Git. That assumes that you have Git installed. And you can either use the yes, I'm showing the link right here, so I'm copying and pasting. So here you can click on that link or copy and paste this link inside this box here and choose the project directory name and then create project. So this option will work well if you already have RStudio and Git installed. If you do not have Git installed, instead you can do a different strategy. And here you will do sorry, I just have to do always this dance between the different screen sharing. This one. Here we go. And so here, the other option is to click to go on the same URL and then click on code and download zip. And then you'll be able, when the file is downloaded, you can expand the file in a directory and then point RStudio to that directory, and then everything should be set up. So I'll let you do that in the background. And at the end, you should have a directory with this code.r file and this data folder. The data folder contains a single file, which is a Parquet file. And then this code.r file that right now has just these few lines of codes. And when we are in the live coding section of the tutorial, you'll be able to open this file and type the code along with me that we are going to use. The last thing I want to mention is that we're going to need two packages today for this tutorial, DuckDB and dplyr. OK. Excellent. So let me again switch screen. Here we go. And before I go too much further, if do you have any trouble right now that prevents you from starting the download or have a hard time accessing the GitHub repository? And if you do, you can use one of the reaction button, maybe like the red cross or something, or type directly in the chat, and I'll see if I can help you. I'll give you just a few seconds in case someone has an issue. And if everything is good, you can also give the thumb up, and so I know that everything is good. OK, I don't see anyone mentioning having any issues so far, so I'm going to keep going. And then in a little while, before we start the live coding session, I'll check in again, and we can troubleshoot if there are any issues. OK, so first I want to start by showing some resources. I'm going to put it at the beginning of the presentation. So I put a few links about how to learn more about using R and Arrow. One very great resource that has recently been published is this book called Scaling Up with R and Arrow. It was written by Nick Crane, Jonathan Keane, and Neil Richardson. And the book is not available in print yet, but it's available for free online. The link is in the presentation, and I'll share this presentation with you after the tutorial is done, so you'll be able to find it. And today, in the live coding section, a lot of the code and the data set that we are going to use is coming from this book. So I want to thank the author of this book for creating this great data set that we can use today. There is also a great tutorial. It has been given a few years in a row at POSITConf. The latest version from this year is there. There is a link in the presentation also. And it's, I think it was a half day, maybe even a full day tutorial. So there is a lot of material, a lot more than what we'll cover today. But it's great to go a little bit deeper in how to use Arrow with R. The documentation of the R package is also good, and it's a great place to get started. And Nick Crane also had started the Arrow R cookbook, and it's also a good resource to find some code snippets on how to do different things with Arrow. For DuckDB, there are not as many resources right now because it's still, I think, a pretty new tool. And I think the people who use it tend to already be familiar with how it works. And so there are not a lot of tutorials yet on how to use it. But maybe that will change. And so the resources I'm giving here are more geared toward DuckDB in general, not so much the interaction with R. But there is this book called DuckDB in Action. And if you go on the Mother Duck website, you can put your email address, and they'll send the book for free to you. The DuckDB documentation is also very good, and there are some great examples, good code examples, and also a good section on how to use R with DuckDB. And there is this GitHub page called Awesome DuckDB with links to lots of different projects that use DuckDB, and it's a good resource to explore as well. I just want to talk very briefly now about the dataset we're going to use. We are going to use what is called the American Community Survey Public Use Macrodata Sample. It's a little bit of a mouthful, and but it's a very interesting data set where every year the this organization, the American Community Survey, goes door to door in the US household and asks questions about the people who live there, about the type of housing they have, their origin, the type of or the commute to work, or long is their commute, and lots of different things. And so it's a very rich, very dense data set, and it's been collected, as I said, I think every year for some of it, and then every 5 years, they do even a much larger survey that has even more data. And so you can download all of this data for free. It's in a format that is a little hard to work with as it comes. But today we're going to use a version that the author of the book I mentioned before have prepared. And this is more ready for analysis with a lot of data cleanup already happened. And so that will be helpful to work with. I think it has a few hundred columns in this data set, and they all use abbreviations. And so it can take a while to figure out what are in each of the columns. And so they have this big web page that is a variable dictionary that we'll refer to later, that gives a brief explanation of what each of the variables are in the data set and what are the values in each column. And I also included a link here about some reading you can do if you want to learn more about this data set and what you can do with it. So let's go back to we focus really of the tutorial, and it's larger than memory datasets. So if you've ever seen a message like this, or maybe your R session aborted because you tried to import a dataset that was too big for the memory. And really, I want to start by what does that mean to have a dataset that is larger than memory. And to really understand this, I want to put things in the context of a little bit of computer works. This is very simplified, but it's a good mental model to understand what are the different components and what you need to think about when you want to start analyzing datasets that are larger than memory. And so really the 4 or 5 components we're going to deal with today are the user interface. And the user interface is really how you as a human write code or instructions to interact with the data that is on your computer. The engine is going to be the core part of the system that is going to process the data. So it's going to get the data either from storage, so data that is stored as a file on a hard drive, either on your laptop or somewhere on the cloud, or it's going to interact with data that is already in memory, so that is in the RAM of your system. And thinking about these 3 layers and these 4 components is really going to help you decide what is going to be the best tool to analyze your data, and you're going to structure your analysis to take advantage of the benefits that tools like Arrow and DuckDB provide. So again, the user interface is how the users are going to interact with the data. The engine is how the computer is going to interact with the data. And then the bottom layer with storage and memory is where the data lives. And so let's start with a small example of what happens when, as a user, you type read_csv mydata.csv. When you type this, you write R code that is going to, in turn, call some internal C++ or other internal R function that are going to interact with the CPU of your computer to read the my_data.csv file on your hard drive, and it's going to put this data into a new representation that is going to fit in the memory of your computer. And then when you're going to use, for instance, dplyr or any other base R function or things like data table, you are going to use the dplyr interface with the dplyr verbs that we know and love, like mutate, select, group by. And these, in turn, are going to call some internal code inside the dplyr package, which for dplyr is written in C++ most of the time, which is going to interact with the data stored in memory in the format that is specific to R. And this interaction is going to then bring back the result to you as the user. But what happens if your file gets too big? It's a little bit like this truck that is too tall to fit under this bridge. Things break down because your data set is going to require more memory when it's represented inside the memory than you have on your computer. And so you won't be able to represent the full data set inside our memory, and so you can't work with it. And so typically, when you have this type of situation, you need to switch to a database system, because databases have been designed to deal with this very large data set. Instead of having all the data at the same time inside the memory of the computer, instead data is represented and stored on the disk. And then when, as a user, you write some SQL query, it's interpreted by the database system you are using. And here, this is the logo for the Postgres system, but most databases work the same way. Your SQL query is going to be interpreted. It's going to look up the data on disk and put some in memory, keep some on storage, and in the end create a representation of the data that the engine can work with, and that is going to give a result to the user. And a great thing in the R ecosystem is that we are not really stuck with writing SQL, because there are packages like dplyr that allow you to use the dplyr syntax, but call the database engine. And so instead of writing SQL to interact with data, you can write R code, like the dplyr code that you already normally use on data frames that are in memory to work with these very large data sets. And this has been around for a few years, and there are already what I call drivers to work with using the dplyr syntax for data stored in many different database systems. Here again, I put Postgres, but there is MariaDB, there is Mongo, there are a lot of options that allow you to connect to many different database systems to work with these very large datasets. And today, we are going to really focus mostly on DuckDB, but it's a little bit the same idea. We have this option in R to use the same syntax that we know from dplyr to work with data that is going to be too large to fit in memory, and that is going to use the DuckDB engine instead of using the dplyr engine that we would use with regular data frames. And it's very similar situation if you are going to use Arrow, because here the engine is going to be things that come with the Arrow package instead of being the dplyr syntax. And so I think what is interesting or good to know at this point, to keep in mind, is that we are used maybe of thinking of dplyr as a single entity, but really dplyr, the package, provides two things. It provides the verb as a syntax that we use to interact with data, and also the computing engine that is going to interact with the data. And the great thing with dplyr is that it's built in a way where you can dissociate the way you work with the data, like the instruction that you give the computer, like the verbs you are using to interact with your data, and what is going to do the computation and what is going to interact with the data. So if you just use dplyr, it's going to be the C++ code that comes with the package. But if you couple dplyr with DuckDB or Arrow or any of the dplyr supported packages, or sorry, database systems, then you are going to switch where the computation is going to take place, and it's going also to influence how the data is going to be stored and where it's going to be stored. And if you remember the diagram I showed earlier with Postgres, it's the same basically with DuckDB. So what is a big difference about using a system like Postgres and using something like Apache Arrow or DuckDB? Well, the first is that inside the memory of the computer, the data is not represented the same way. So in regular database system, the data is represented what is called row-oriented. So next to each other in the memory of the computer, you are going to have the content of column 1, column 2, and column 3. And so, and then once you are finished, we are done representing all the columns of your database in the memory, then you have next to that the second row of your column. And so you have row after row being represented in succession inside the memory of your computer. And this type of layout is great when you are dealing with a database system that wants to record, for instance, the transaction in your online store or the user or information about users, because the information about an online order or the users are going to be close to each other in the system. And so it's easy to add information or remove information because you keep adding more data in this row of memory. But the problem is that when you want to do analytics on this type of data, then if you want to analyze column 1, for instance, you are going to have to scan all the data to find every single places where you have the column 1. On the other hand, systems like DuckDB or Arrow are already designed to analyze data. And so they use a system that is already familiar maybe to you as an R user, where it's column-oriented. So all the data from a single column are close to each other on the memory. And that means that it's much easier to do aggregation, for instance, because if you want to calculate the mean of column 1, all the data about column 1 are very close to each other in memory. And so the computer can quickly find it and summarize it. And so the column-oriented design that DuckDB and Arrow provides make analytics operation much faster. It's easier to select just column 1 or just column 2 because they're close to each other in memory. Again, if you wanted to do the same thing with a row-oriented design, you will have to scan a lot more data to be able to find it. And again, if you want to do if you want to compute the mean or the median or any type of summary statistics on this data, having all the data close to each other in a column-oriented format makes it much faster. And another benefit is that, again, Arrow and DuckDB work the same way. They can work on different parts of the file at the same time because the memory layout makes the data separated. You can use your CPU to analyze one part. One core of your CPU can analyze column 1, one different core of your CPU can analyze column 5. And then when you do the aggregation, you can do it at the same time. In a row-oriented, it's much more difficult because you have to scan the data multiple times. And so this parallelism is not as efficient as for column-oriented data. Here you go. So to summarize, when you want to work with data, and especially larger than memory data, I think it's really interesting or important to think about these 3 questions when you start designing your code and your analysis. You are going to decide how do I interact with my data? Are you going to write R code? Are you going to write Python? Are you going to write SQL? And then what is going to process my data? Are you going to use something that works fully in memory, like the plain dplyr engine or data table, or are you going to use something that allow you to process data in both storage and memory, like Arrow or DuckDB? And obviously, your type of processing engine is going to also affect where the data is being processed, whether it's just on your hard drive. I think it's never just on the hard drive, but is it just in memory, or is it a combination of both storage and memory? So to try to answer these questions with DuckDB, I tried to answer this question with an example of using DuckDB. So how do you interact with my data? If you are in R, you will be able to write pure SQL code or write dplyr syntax. The processing engine is going to be the DuckDB engine. And where is my data? Obviously, the CPU works with data in memory, but DuckDB is designed in such a way that it never fully saturates the memory. And if DuckDB needs to work with more data than fits in memory, then it's going to write some of it on your hard drive. So it never fully saturates the memory, and you'll be able to work with larger than dataset data. This is called like a streaming engine. It's a little bit like watching a YouTube video, for instance, where the computation engine for your query is going to look just a small section of the data at any given time, and doesn't need to have the full representation of the data and memory to do the computation. And so that's one of the ways DuckDB and Arrow allow you to work with memory that is larger than memory. So we talk a lot about the different components, but I think it's also important to talk about how are you going to get this data into these systems, into DuckDB or Arrow. And so both Arrow and DuckDB can deal with data that is stored as CSV file or JSON files and Parquet. DuckDB has also extensions, and some of them are developed by the community. And so, for instance, recently someone came up with an extension to work with DuckDB as an engine to connect to data that is in Google Sheets. It also has an extension to work with files called Apache Iceberg, if you heard of that. And so there is a lot of different file formats that both DuckDB and Arrow can deal with. And both of them also can deal with data that is either stored locally on your laptop, on your computer, on your home server, but they also can connect directly to data in the cloud that is stored on AWS S3, Google Cloud, or Azure. And because of this raw-oriented data format that I mentioned earlier, that also make it in a way where you can, you don't need to download the full data set on your laptop before Arrow or DuckDB can work on it. They can only select the data that needs to be downloaded to do their manipulations. And so it's an efficient way of working with data in the cloud. And the last thing I want to mention is that if you're working with very large data sets, files like Parquet offer the option to have them partitioned by a variable. And so it creates this folder system where the data is split into multiple files that represent different segments of your data. And so, for instance, if you have collected a data set over several years, you can split your data so each year in its own folder, and you don't have to worry about telling DuckDB or Arrow exactly the structure of the file. Like, as long as you follow this standard format, they will be able to find the data set just for the year you're interested in, allowing, again, to not use the full data set, but just focusing on just the data you need for your particular query. Because it's going to be a short workshop today, a short tutorial, where we won't have an example of the Hive partition, but if you go to the Apache Arrow tutorial from POSITconf that I mentioned earlier, you'll be able to have some example of that. Yeah, and before we start going on the hands-on, I just want to mention a little bit about Parquet files. So Parquet files are a great way for storing data. Again, they use the column-oriented design to store the data, which is going to make the analysis much faster on them. Again, because we can just select one column, we can have the CPU working on different parts of the files. And so that's a very efficient way of storing the data. By default, the Parquet files are compressed and encoded. Basically, they use some of the same techniques as like the factors in R. If you have a column with a lot of if you have different values as text in one column, they are encoded as unique representation, and so you don't have to store every single value the same way you will do in the CSV files, for instance. The data are typed, which means that each column has a defined data type, for instance, a date, a string, integer, and of different sizes. And so it makes it that you can store, again, data very efficiently inside the Parquet file. And because the layout of the Parquet file is on disk is very similar to what the Arrow or DuckDB uses in memory, it's very fast to read these data files and convert them to be used in tools like DuckDB or Arrow. And so if you're not using Parquet files yet for your data, I really encourage you to explore this. It's a much better option than CSV files, because when you share it with someone, you can be sure that the data types are going to be stable and are going to be able to read the dataset exactly the way you intended it to. Okay, so I think we are done now for the lecture, and we'll be able to soon switch to the coding. But I wanted to check in at this point to see if anybody had any question at this point. And if you do, please write your question in the chat, or feel free to unmute and ask your question aloud. During this time, I'm going to switch to have RStudio open. Okay, wait a few more seconds. Okay. And again, also before we start here, please let me know if you have any trouble accessing the content of the repository, whether you download it using the Git method or using the zip file. I'll wait a few more seconds just to make sure that no one has any issue, and then we will get going on the coding part. And can I please have a thumb up if the size of the RStudio window, the font is big enough for you and you can read without any problem? Perfect, thank you. Perfect. Okay, so it looks like we can get started. So just to make sure, you should have, if you use RStudio, it should look basically like this. Your working directory should be where this code.r file is, and there is a subfolder called data, and inside this subfolder, there is this Parquet file in there. Oops. I'm going to minimize this so there is a little bit more room to see the code. OK, here we go. Let's see. So we're going to just start by loading the DuckDB package and dplyr. And again, because our time is pretty limited today, I really wanted to focus on just one language. And so I'm going to mostly give examples using DuckDB, but a lot of the way of working with DuckDB is very similar to what is done with Arrow. And again, the tutorial that that was taught at POSITConf this year has a lot of great resources. So if you want to have a more in-depth exploration of using Arrow, I really encourage you to go check that out, because it's really good content. So to work with DuckDB, first we are going to need to establish a connection to a database, a DuckDB database. And the way to do this is to create an object that we're going to call con, like connection. And we're going to use a function called dbconnect. And dbconnect comes from the DBI package. And it's a package that allows you to interact with DuckDB, but a lot of different databases. And so the first argument that dbconnect takes is the function that is going to allow you to connect the driver that is going to allow you to connect to the database. And for DuckDB, it's simply the function called DuckDB. And to start, we are going to type :memory:, and that means that we're going to work with a DuckDB connection that is going to be inside the memory. So this is a great way to work in a way that is non-persistent, which means that you are going to use DuckDB really as an engine. You are not going to store data in a persistent fashion on your hard drive. And it can be very helpful to get something going quickly to rely on using this memory setting. But later on, we'll work with persistent storage, and I'll show that a little bit later. And so when we evaluate this, we don't get any output. We just get this evaluated. We can type the name con here to see what it looks like, and it tells us that it's a DuckDB connection using the DuckDB driver that we are in memory. And here we are read-only equal false, which means that we are going to be able to obviously write data to this connection. And it can be helpful if you are, for instance, using DuckDB inside a Shiny app or something like that, to use read-only equals true, where people are going to be able to interact with your data, but without writing any data to it. And that allows you to have multiple people connected to the same data. If you do read-only equals false, then only one person at a time can work with the file. OK, so once you have created the connection, we can use the tbl function that comes with dplyr. The first argument it takes is a connection to the database. So here, just con. And here we are going to use this approach where we're going to type read Parquet with single quotes, and we are going to type the name of the path for the Parquet file that we have in our data folder. And by doing this, what it does is that it's going to use the read Parquet function, or the Parquet file reader that comes with DuckDB. And that's a way to load the dataset lazily, which means that we are not actually to read the full dataset in memory to be able to work with it. And here again, it doesn't matter too much because the dataset is not that big and it fits, I think, in most people's computers' memory. But if you were dealing with a very large dataset, that would be an issue. You wouldn't want to read the full dataset in memory. You want to take advantage of the fact that DuckDB uses this lazy evaluation where it can look at the file and have a pretty good idea of what's in it by scanning just a little bit of the file without having to materialize the entire data in memory. So to check that it worked, we can pipe the output of this function to head and see what we have. Sorry, I had read Parquet selected, and so it was not working. But yeah, I'm doing this, and it's not working. Oh, did I type the file wrong? Because I think I changed the name at some point. Oh, it's personal. That's my bad. OK, I'll have to remember this. Let's try this again. OK, this time it works. And so if we look at the output here, a bit higher, we see that we are dealing with DuckDB database, and it shows us the first 6 rows of these Parquet files. You can see that it has 311 columns, so it's a pretty wide data set. And here we are seeing the first 6 rows. Again, it shows that we are reading the data from memory. Well, we are using, sorry, the memory setting to interact with the data. And yeah, just to give us a quick overview of that file. If we want to get all the column names, we can use the copy and paste here, so we can have an actual record of what we did during the workshop. And we're going to use the call names function. And here it outputs the name of all the columns in this database. One thing to note is that while the head function works, the tail function doesn't work, because in a database setting, because we're using this streaming approach, because we don't represent the full dataset in memory, the notion of what it at the end of the data doesn't make sense. The database system cannot figure out what is at the end of the data, because we are just streaming the data. And so we'll know that we are at the end when we are done reading the data, but not before. And so it's something to keep in mind, that we can look at the beginning of the file, but not the end of the file, because the end of the file in database setting is, yeah, it doesn't really make sense. Another thing we can do is to figure out how many rows we have in this data. Again, we cannot really use nrow, because nrow works for data frames, but not this type of connection. But count, without any arguments, will give you the number of rows in the data set. Yeah, and so here we are dealing with 481,323 rows. There was a question from Bastian: why does a file reading function has to be written as a text string? Very good question. So this, under the hood, is really actually a DuckDB code. And so what we put in quotations here is a a request that we are making to DuckDB. This is not actually our code. This is DuckDB code. And so that's why we need to put it in quotation, because we are asking DuckDB to read this file for us. When it's also because DuckDB tries to be smart about things. And so normally when you use a table function, and we'll see that a little bit later, you are specifying the name of a table inside your database. Here, our database is empty. We haven't put anything in it yet. And so when you give the read_Parquet function to DuckDB, it knows that it needs to read that file and not try to look for a table named read Parquet. Does that answer your question, Bastien? Perfect. Okay, so another thing we are going to look at is what is the distinct values in the ST columns. The ST columns stands for state. Again, it's a small slice of this data set. And so we only have 7 states represented in this data set. These are the states we are going to work with today. We have Alabama, Alaska, West Virginia, Wisconsin, Arkansas, Wyoming, and Arizona. And we also have different years. I think we only have 2 years for this. We have the year 2018 and 2021. So for each of the 7 states, we are going to have, two years. And if we want to see how much data we have for each of these combination, we can do this. Instead of doing distinct, we can do count of state and year. Oops. And so it varies, obviously, depending on the state. But we have between 73,000 and there's a smaller one are like in the 5,000 range. Let me make this a little bit bigger. I don't know if you noticed, but I want to point out a few things. If we look at the output of this distinct, if you are familiar with dplyr, you might notice that this is a little bit strange because typically when you are using the distinct function, this data is going to be ordered by state first and then the year. And here we can see that we have Alaska, Arizona, and Alaska again. And it's not something we would see if we are using dplyr. Again, another thing strange is that here it gives us this double question mark instead of the number of rows. And if we look at the output here, we see a similar output. Again, we have this double quotation mark here. And here the order is yet different, even though we specified state and year, just like distinct state and year. And so this is a little bit like the same reason why we cannot have a tail function when we're working with databases, is that the order in which the file is going to be read and the data returned to us is going to be random. Because the way DuckDB works is going to scan the data set with your multiple CPUs at the same time. And so the way in which the data is going to be computed and returned might differ from one time to the next. And so if the order of the output matters to you, you are going to need to specify which columns you want the data ordered, which column you want to use for ordering your data. Okay, and and the actual number of rows, we don't have it because when we do this type of requests, Again, DuckDB doesn't actually compute the full results. It just computes the first few rows to show us what it looks like. But we need to specify that we want the full results for it to do it. Otherwise, it's just going to give us the first few rows. And that's a way to speed up the computation, make sure that things work without spending a lot of time, and also not wasting a lot of memory if you're dealing with very large datasets. So let's do that again. Let's show this again. So we are going to, if we wanted to see the output in a specific order, we will need to add a call to arrange and specify that we want the data ordered by state and then year. And then when we do that, then we have the data as we expect it, with state organized by alphabetical order and the year in increasing order. And again, here we haven't computed all the data. We still have the double question mark. If we want to do that, we will need to add a call to the function called collect. And collect will tell DuckDB that we want the full result. And so here, instead of just doing the first 10 rows, it will do the computation. And what we just asked here is giving us 14 rows. OK, I'm going to pause just for a second here to see if there are any other questions so far on what I've shown. Looks good. OK, we're going to continue just a little bit longer, and then we'll take a short break before we continue on the coding. OK, so let's look a little bit more at the actual content of these files. So here we looked at the number of rows we have for each state and each year. And we got this number. Do you, I don't know how familiar we are with the geography of the United States, but you can see that these numbers are probably too small to be the actual population of Alabama or Alaska. And this is because the way these census files are structured is that each row doesn't represent an individual, but a group of individuals with similar characteristics. And so they provide a column with a value in it that represents the number of individuals that share the same characteristic as all the information that are in that file. And so if we want to get a number of people, we need to do the sum of this column. So let me again just start here. I'm going to just copy and paste the first line so we don't have to I don't have to mess up the path for the file name. And so we are doing, we can do a summarize. We're going to say n, and we're going to calculate the sum of the pwgtp column. And we are going to use the .by argument to say that we want the sum made by year and state, just like we've been doing it. And again, to keep the output consistent, we are going to use the arrange function, where we're going to specify again the state and the year. And again, if we do this, first it tells us that there are some missing values in some of the pwgtp states. If we were in dplyr or base R, the result would be NA. But because we are dealing with a database, that's the default behavior. And so even if we don't specify n.rm equals true, the results of the aggregation, like the summation of this column, is going to do the same thing as if we had put it. But we can add it so we don't have the warning message next time we run it. OK, here it is. And so here, the numbers we get are closer to the actual population sizes for these states and these different years. Again, we didn't call the function collect. And so again, it calculated the first 10 rows and stopped there. If we wanted to get the full data set, we wanted to add the call to the collect function to get the full calculation done on all 14 rows. So yeah, here really what I wanted to show is not so much details of the data set, but more that if you already know to use dplyr, you can work with DuckDB pretty easily because the syntax, for the most part, just translates seamlessly. We didn't have to learn anything new, really, rather than this first line, which instead of referring to a dataset in memory, here we are using the Parquet reader from DuckDB to read the content of the file, and then the DuckDB engine to do the computation. Again, here we are using the same syntax as dplyr, but under the hood, dplyr doesn't do the computation. All this computation is done internally by DuckDB. And one example, or one way we know that is the case is, for instance, this behavior of the sum function that dealt with the missing values differently than it would have done it if we were dealing with the dplyr engine. Yes, let's take a little break here for maybe just 10 minutes before we continue doing a little bit more coding and a few more examples. I think next we are going to switch to using a persistent storage, not using just the data in memory. And then we'll look at some more advanced function usage. If you have any question during this break, feel free to add them to the chat, and I'll see you again at 15 past the hour, or in 10 minutes. I think everyone is in a regular time zone, but yeah, in 10 minutes from now. So see you in 10 minutes. Welcome back, everybody. Okay, so we had a few questions. Perfect. Let's look at them before we continue. Yes, so there is no slice function because, again, like the order of the data inside the DB is not determined. And so there is not a row 123, for instance, like that doesn't really exist in the way DuckDB works. But there is a slice n function that exists. I'll make a note of it and find it. I don't want to say anything wrong at this moment, but I'll look for it and get back to you. Let me make a note of this so I don't forget. Okay, perfect. Suppose as a wrong format, codified as text, transform it with some of these functions. Is it only possible to modify its original database? Yes, so that's, in theory, if you have a Parquet file, for instance, if you create the Parquet file, the person who created the Parquet file should make sure that the data type matches the actual content of the column. But I can see a situation where there might be a situation where the data is coming from a CSV file or something happened and we got the wrong data type. So it's possible to use, I think internally, the cast function, like you're using in SQL to convert the data type. I've never encountered this issue, so I don't know if there is a way to do it directly with a mutate call. But again, I think it's something I can look into and try to find the answer. Mutate for type change. Excellent. And Moro, we use SQL to get to. Yes, would it be possible to use analogous SQL to do this operation before collecting the results? That's something we are going to show how to do a little bit later. Right now, we have been focusing on using what is a dplyr syntax to interact with the data. But because we use the dpi package, we can actually send raw SQL directly to DuckDB. We don't have to do that. We don't have to use the dplyr function. And in some cases, like if you had to change the data type and used SQL, the cast function, sorry, to change the data type, to transform the data type, then you need to use SQL to do that. And I thought I had seen. Oh, and use libredate function. I do remember I had said something about libredate. Yes, so we saw this a little bit later too. So today I really wanted to keep it simple because we only had 2 hours and don't overwhelm you with lots of different options. But I only showing you the package called DuckDB. But there is another package that is called duckplyr. That works a little bit differently. DuckDB works the same way as other packages that interact with databases, whereas the dplyr instructions are internally converted into SQL code, and then this SQL code is being sent to DuckDB that interprets it to do the manipulation it needs to the data. This other package called duckplyr doesn't work the same way. They directly mapped the dplyr verbs to the internals of DuckDB directly, and so we skipped the conversion to SQL step. And I think in this case they are working on adding more and more function, and I think some of the libredate functions are directly mapped to the internals of DuckDB, because DuckDB has a lot of functions to work with dates and times. And so this mapping makes it more direct. And I do think that some of the liberate functions are also mapped to SQL. And so I think some liberate function work also directly the way we are doing it today. But if you are working with more complex operation with libredate, I know that recently I was working with something where I needed to find the last day of the month for the current date, and it's something that was easy to do in libredate, but that was not supported directly in DuckDB, and so I had to go through the SQL version of that call to make it work. But yeah, thank you. All these are great questions, and I'll add them to. I'll make sure to find answers to the two questions I didn't answer right now, and I'll put them in the README or in the code I will share after the tutorial. Probably I'll put it online tomorrow. Okay, great. I think I'm still sharing my RStudio screen. Let me see if it's the case. Yes, it looks like it's the case. So let's continue. Or let's keep a little bit of output here. Sorry, I need to reorganize my screen space to see everything at once. I see that the time is ticking, and so we are going to keep moving. I had more examples I wanted to show you, but it was just to reinforce this point where it was more complex examples of using just the dplyr syntax to work with DuckDB directly. I'll put them online in the notes, and so you'll be able to see them. But I had an example with a case when, for instance. Case when works great with DuckDB, the DuckDB package, gets interpreted directly into the SQL, and you can work on it directly. But let's skip to the next part where we want to work with actually permanent data. Because so far, if you remember, we have been working with this con object, which we define at the beginning here, and this is working in memory. So, and everything we've done so far is very exploratory. We are just trying to look at very simple query about this data set, trying to figure out how many rows there are, and we just showed you how we can calculate the number of the population size in each state for the 2 years we have data for in this data. But if you want to do like some more complex queries, maybe you don't want to have to redo them every time. And again, here we're working with a small data set, but if you're working with a much larger data set and the computation takes a little bit of time, even if it's just 1 second or two, you maybe don't want to have to recalculate every time. Instead, we can make it persistent and not use the memory setting of DuckDB, but instead write the content to a file. So we are going to first use a DB disconnect to close the connection we were having, where is the one on memory, and we're going to create, and we're going to create a new one where it's going to be exactly like before, where we do db connect and DuckDB. But here, instead, we are going to use a dplyr argument to specify where we want the data to live. And so let's create a small database, and we're going to call it PUMS. Again, PUMS is the name of the acronym of the dataset we are working with today. It's small, so we're going to do PUMS poll, and we're going to give it the DuckDB extension. Yeah, and so another great thing about DuckDB is that not only it's a single file when the executable is a single file, like you don't need a complex installation to get DuckDB to work on your computer. It's also very easy to share files, DuckDB files. If you're working with other databases like Postgres database, like the storage that it requires is this complex system of files and folders, and it's not like you can put it on a USB drive and share it with your friend. A DuckDB file is something you can share with a friend because it's a single file and it contains everything you need to work with it. And it's even compatible across version, especially since the last release of DuckDB. And so you know that the format is stable. And so even in a long time, like several years from now, you should be able to use the version of DuckDB at that time to open the file you're going to create today, and it will work. It will have everything you need. And we can just to be safe, we're going to say read only equals false, meaning that we are going to want to add data to this file. We are going to evaluate it. Again, no output here, and just by curiosity, we can look at the output. And here, it looks very similar to what we had before, except that this time, instead of being memory, we have the actual full path to the file we just created. And I believe that if we look in our working directory, yes, the file was created. It's empty right now. There is no data in it, but the file is there in our working directory, and we are going to be able to start working with it. Okay, so up until now also, we have been reading the data every time we wanted to do something. And again, here, the data set is not that big, and so it just took a few milliseconds. We didn't notice that in the background, DuckDB was actually reading the whole file and doing the computation because the file is not very big and because DuckDB is also very fast. But if we wanted to work with data, real data, we want to create a table directly inside DuckDB. And so there we have basically a few approaches. I'm going to show like the pure SQL version of it now, because it's one that is going to scale well even to very large data sets. There are a few other ways of doing it, but again, this one is one that only uses the DuckDB package, and that will work even if the data set is very, very big. So we are going to use the db execute function. The db execute function comes with the dbi package, and as its name implies, it's going to execute a SQL statement inside the database. So it takes, again, con as the first argument, so to tell it where the instruction is to be sent. And just for readability, I'm going to put a new line so you will have the full line. It's a relatively long one. So we're going to use a SQL statement where we're going to say create table. We are going to call it pumps person small, and it's going to be as select from, and we're going to use again the read Parquet function as we did earlier. And I think I'll try to clean this up also when I share the code on GitHub, so there is not like this person and personal difference. It was my mistake because it's person, not personal. Here we go. So this takes a few seconds. It takes a few seconds because a lot of things happen behind the scenes when we do that. Obviously, the full dataset needs to be read, but even if it was very large, it doesn't put everything in memory at once. It uses streaming mechanism, and so it reads by batches. But it needs to create a table, and it needs to infer the data type of each column when it creates the table. And so, yeah, it took like maybe 2-3 seconds to create that. The output of the db execute here is a number of rows that were created in this case. And so we see the same number of rows that we saw when we did the count function earlier. Just quickly, we could have also, and I'll show this I think later, read the data in memory and then wrote it, but if the data set is big, then it could exhaust your memory and you can run into trouble. So we didn't use this approach. And we can use DB list tables to see what we have. Sorry, I need to drink more. To lose my voice. Okay, so if we use a DB list tables function, as its name indicates, it tells us the tables that are in our database. And right now we have one table, which is the pumps person small we just created. Okay, so to show a good example of what you can use persistent storage for, we are going to create another table inside our file, and we're going to do a join between the two. And to illustrate this, we are going to create a table that is going to calculate the mean commute time for people by state and by year. And then we do a join to compare the deviation from the mean for the different states. Okay, so let's start by building our query. Here we're going to use a table function again. We specify again our connection, but this time, because the table exists inside the database, we don't need to use a read Parquet function anymore. We can specify the name of the table directly. And so our table is called pumps person small, so we can do pumps person small. And we can use a summarize function to calculate the mean commute time, which is going to be the sum of this column called J, W, M, and P. And we need to multiply it by the weight, the number of people that are in the same category. That is P, W, G, T, P, divided by sum of P, W, G, T, P. And we need to aggregate by state and by year. Let's see what it looks like. And so here we calculated our commute time, or average commute time by state and by year. So if we want to create a table inside our database with this information, we can assign a variable to this. So mid commute time. And we need to, here, we're going to collect here also to have all the data we want. And again, this is a small, this is going to be a small table, so we can do that. We can do everything in memory. There are only 14 rows, just a combination of states and year. And we can use a db write table function to include this data into our file. So we again specify the connection, the name of the table. We're going to call it mean commute time. Oh, yeah, sorry, mean commute time. And the name of the variable that has the data for it. Again, it was a small data, so it was pretty fast to write. And we can do DB list tables again to see the tables in our database. And now we see that we have the one we created earlier, that has a full data set, and this one that has just the aggregation of the two. And just to show that it's actually inside the file, we could do first we can check what we have it. We can do table con of mean commute time, and it will show the beginning of this table. So that looks good. And just to simulate what will happen if we were to, let's say, close the session. So we disconnect, we even, let's say, remove the object. So there is no trace of that connection to our database file in our memory. But we can recreate it. Here we go. And if we do db list tables again, here we see that we have our two tables, and I'm going to be just recording this, and we can see that the table is still there. So what I just did here was just to simulate what would happen if we closed our session and reconnect a different day. The data is there, it's in the file. Even we can look in the file explorer here, and we can see that it's much larger than before. Before it was just 12 kilobytes because we had just created the file. Now we have almost 108 megabytes of data into our database. Okay, perfect. And again, if you gave this file to someone else, they will be able to type the same command on their computer and get exactly the same data as you. So just I'm going to demonstrate the join. So let's do table, and we are going to do the small. And we're going to do, oops. I'm going to do a left join on this other table that we just created. It was a mid commute time, and we're going to do the join by state and year. So what does that do? It's going to be hard to see if we just have all the columns here. So I'm going to first select just the column that we care about. We want to see the state, we want to see the year, and we are going to want to see the actual commute time, which is in the GW, M, and P column. And we also want to see the mean commute time column that we created. That should be more indicative. Yes, that's better. So this is just the beginning of the table we just created, joining these two tables. And we see for each person their commute time. So this group of people commuted for 5 minutes, while the average for the state and that year is 8 minutes 67. And so, yeah, if we wanted to actually compute the difference, we will also probably need the PWGTP column that has the weights. And here again, just to demonstrate, but we can, if we wanted to calculate the difference, we can do something like this, where we do the difference between the actual commuting time minus the mean of the commute time. And we probably also, before, we probably want to filter all the people who don't commute, either because they are too young to work or work from home or retired. GW and MNP. Okay. Yeah. So yeah, that, and then we could aggregate, for instance, by year and state to see which. Oh, sorry, that's not what I'm going to say. So here it gives us the total the difference between the mean and the actual commute time for all the rows in our dataset. And for instance, if we wanted to compare or look at which type of work people do and how it impacts their commute time, we could do this with the dataset because there is a column called OCP that also has the category of work that people are doing. So let's look at this really quickly. And you can see that it's one that has maybe a few hundred different combinations, but they're categorized by big groups with this 3-letter code. And so my idea here was to see if we could look at this extract this 3-letter code and see if there was, or explore, or the type of work based on this big category, the 3-letter code in front of the occupation, impacts the commute time. And so up until now, everything we've done, we have been able to use straight up dplyr verbs or functions to do the type of analysis we wanted. But here we're going to deal with something where it doesn't work, and I can show you what we need to do in this time. So for instance, we may want to do something like to mutate, where we do occupation. Check a second. That's occupation or category. Let's go this category. And we could use maybe the stringer function called string split I, where we would give it the name of the columns with the occupation in it, and we want to split on the dash, and we want to get the first part. What happens if we do that? Then we end up in situation where the dplyr package doesn't know how to interpret this function from the stringer package, and doesn't know how to translate it. And so depending on the situation, we could try to do the collect first, because once we collect, it means that the data is going to be in our memory as a data frame, and then we are going to leave the DuckDB world and enter back into our dplyr world. And so in this case, this call will work. But maybe you need to do this before on a very large data set, and you need to do it before aggregation, and so that wouldn't fit in memory. And so we may need to find another solution. The solution here is to switch back to using SQL. And so I'm going to keep this here, so you will have the example. But we can do category equals, and here we use a SQL function. And so what that does is that dplyr is going to recognize it as raw SQL that we are sending straight to DuckDB. And so here we are going to actually not use a function from the stringer package, but directly a function from DuckDB itself. And the equivalent function to that is called split part. And it works almost the same way as the stringer function. We provide the name of the columns. We provide the characters we want to split on, and the part we want. DuckDB, just like R, is to index at 1. And we need an extra. I think what else is wrong here? Yeah, I think everything else should work here. What happens if we do that? And here we have the outputs that we expect, where we have the first part of the occupation column, the first three column, whatever is the first three character, whatever is before the dash. And again here, the split part function is not a function that belongs to dplyr or on, but one that belongs to DuckDB. And let's take just one quick second we're going to leave RStudio and we're going to go to the DuckDB webpage to show you where you can find this, this function. Just 1 second that I change the screen. Oops. Share, new share. Okay. If you go to the DuckDB website, you can go to the documentation, and you can go to, yeah, SQL, I think will take us here. And under function here, you have all the functions that are organized by the type of function. And so here we are manipulating text, and so you can go to the text section. And here are all the DuckDB functions you can use to modify or extract text information from a column. So there are quite a few, some that use regular expressions, some to reverse the strings, to add padding to the right, to the left, or to split the strings. Again, there are lots that are available here for text manipulation. Someone was asking about libridate. Again, there are a lot of functions to work with date. Same thing with working with time or timestamps. And really, there are a lot of options here you can explore. And so this combination of using mutate plus this DuckDB function can be very powerful to modify your data. And all of this can be done, again, on very large data sets, because here you are not relying on R to do the modification of your data, but you are using the DuckDB engine. The downside, obviously, is that you potentially have to learn the syntax of these functions, and it's something else you need to learn. But at least in my experience, I have never done anything very too complicated in terms of data manipulation. But the syntax is not that different from what you would be doing in R. Yeah, it can be very fast even for very large data sets. Okay, let me back to RStudio now. And I think I saw a question. Let me go back here. Window, RStudio. Okay. Yes, I believe. I don't know if that's a good question. Let me check where it was. I don't know if it's a dplyr or. Yeah, it's yeah, it belongs to the dplyr package. Okay. Here we go. Okay, we are almost only 10 minutes left, so we're almost at the end of what I had prepared anyways. I had prepared an exercise, but maybe I'll add it in the code so you can do it on your own. I had another, yeah, a little more complex example. The same type of idea is this, using this SQL function works well when you are dealing with simple, small modification of the code that where there is a directly small modification of the code that have directly DuckDB function to do it, but sometimes you may have to fall back to more complex SQL function. So to try to illustrate this, we had the situation where I wanted to illustrate this by showing I'm going to, we could start with using just pure R code, but I'm going to slowly build it using SQL, so it will be easier to understand at the end. Let me make some more room here. Oops, what am I doing? So we are going to use a DB get query. We've seen before the DB execute. DB execute, you use that function when you have a SQL statement that is going to modify something internally on the database. The DB get query is what you use when you want to get result back from a query. So when you do a select statement, typically, you are going to use DB get query to get the result back. So we are going to select again same column that we've been working with. So state, year, and we're going to use this drive sp function, and again the pwgtp function for the weights. And we are going to select them from, I should do this so we have even more room to see things, from the perms person small table. And just to make things clearer, we are going to say we're going to filter out the values that are missing for the drive sp column. So where drive sp not null. So if you're not very familiar with SQL, that will be just as if we had started from this table and use the select function to get the column st, year, drive sp, and pwgtp. And we also do a filter on the drive sp column where the value are not NA. And if we do this, you can see that we get our 176,000 results almost instantly. So really, again, it was very, very fast. And this drive sp column has this interesting metric on whether people carpool or not to go to work. And so they have this numeric value first that says 1, meaning that they drove alone, and then they divide this number by the number of people in the car. So it's 0.5 if you are 2 people, and 0.2 if you are in a 5-seater, and 1.43 if you are in a 7-seater or more. So I thought that would be an interesting exercise to try to compute the mean of the drive sp column by state and year. But right now, this drive sp column is stored as a character because we have all this text that is also tied with this number that we are interested in. And again, this is really just to demonstrate how to do it with using SQL, but it's something we could have done, I think, using the same approach here as just the mutate. But I thought it was a good exercise to also show it directly using SQL. So we are going to change this query to actually extract this number here. Just to make sure it's working, we are going to add a new column. So we're going to say split part, again, drive sp. We're going to here split on the space here. So we're going to do single quotation because we are inside the double. We want the first part, and we are going to call this as carpool. That's the name of the new column. Do this, we can see our new carpool column here, but it's still a character because we
we just modified the string in this column. If we wanted to make a number, we used the colon notation in DuckDB, and I think other database systems do that, where we say the data type we actually want. We want a float, like a number. And when we do this and we do the query again, we can see now that our carpool column is actually a number, and we have this. And so here we can imagine that now that we are happy with this result, we could, I'm going to keep this here so we have a record of it. But let's say that we want to create a new table with this information. So instead of a DB get query, we're going to do a DB execute, because we're going to create a table based on this select. But we need to say that we want to create table, and we're going to call it carpool as, and we are going to wrap this up with parentheses to do this. It shows the number of rows that were created. And now, if we did DB list tables for more connection, we have this new table, carpool, that we just created. And so if we wanted, we could fall back on dplyr and use the connection carpool. And we could do the summarize of the way to call it the CPI, some carpool index. And we can do the weighted sum with the PWG TP times carpool divided by sum the PWG TP. And again, we do the aggregation by state and year. And to make it look prettier, we can arrange by state and year. And finally, we can call collect to get the result. And yeah, and here we can see all different values. The closest this number is to 1, the more people don't carpool, are by themselves in the car, and the lowest it gets, the more the carpool. But yeah, I wanted to, again, it's not so much exactly what we are doing here, but I wanted to show you more the mechanic on how to go from back and forth between using SQL when you need like more advanced data modification, and then the convenience of being able to write this as a table inside your DuckDB file, and then fall back on dplyr to do, or dplyr syntax to do this modification. Okay, so that was most of what I wanted to show you today in terms of coding. Let me switch briefly to the slideshow. And please, if you have any question, don't hesitate to add them to the chat. Or this one? Yes. Yeah, add them to the chat or contact me later if you have any question that comes later. Again, I'll make sure to add the code we wrote today and a few extra things in the GitHub repository probably tomorrow, and also the slides, and my email address will be there, so you'll be able to contact me if needed. Yeah, I hope it was helpful. I just want to finish briefly by mentioning some of the questions you may want to ask yourself when is a good time to use DuckDB. The first thing is really, does your data fit in memory? Sometimes DuckDB is very fast, but not as fast for some data as things like data table or this other package called Collapse. Sometimes some benchmarks show that they might be faster. And so if your data fits in memory, maybe you don't need to bother with DuckDB. You can use something else to do it. But even if it doesn't fit in memory, though, if you are starting to deal with joins and having to deal with multiple tables and having data that is really structured as a database, you may still want to take advantage of DuckDB because it's a very lightweight mechanism to work with databases and tables. And it's very convenient to work with,
and really doesn't have as much luggage with it as other database systems. And do you need to share your data with other programs, other people? Another great thing about DuckDB is that it's very interoperable. This file we created, like the DuckDB file that is in our working directory at the end of this session, you can give it to someone who doesn't know R and just work with Python, and they'll be able to connect to it and work with it, or they can just use a DuckDB command line interface to work with it directly using pure SQL, and that would be very convenient. And again, once the data is clean and ready to use in this format, you can use it to power a Shiny app or dashboards or anything you want. So it's a very convenient system. Yeah, I want to thank you for sticking with me this afternoon. I hope you found it was helpful. I created this short survey. I'm going to put the link in the chat. If you can just take a minute. I think there are three questions that I'm asking, and that would be helpful. That's the first time I'm teaching this tutorial. I didn't do as much preparation as I normally do for this type of content, because I had this bad cold that really knocked me down for a few weeks just before the event. But I'm glad I did this today with you. And if you have any question, yeah, don't hesitate to reach out to me by email. I put my email address there. Yeah, I'm glad it was helpful. Thank you for your comments. And I hope you have a great rest of your day, and that I can improve my Spanish, and next time I can give this tutorial in Spanish. Yanni, is there anything you want to say if you are around?
Hey, no, just say thank you one more time. And I saw that were a lot of questions and comments, so I think that people enjoyed, and I hope that you also have enjoyed the delivering the tutorial, Francois. So thank you so much, everyone. And we are going to communicate to everyone when the video is up. And I hope to see you all during the rest of the day of Latinar.
Sounds good. Thank you, everyone.
Okay. I'm going to finish the meeting now.
Sounds good. Thank you, Yanni. Bye.
Bye-bye.